Hello, everybody. Welcome to lesson 7.1. If you are in AB Calculus, this is your last unit of the year. If you're in BC, not quite there yet. But today we're going to be talking about separation of variables to solve differential equations. So let's get cooking looking at this slightly controversial method of solving differential equations. So our goal today is to be able to solve differential equations through separation of variables. Basically what this means is we can find a general solution to a differential equation or a particular solution. Particular solutions come when we have an initial condition. General solutions are a family of possible solutions that will include a constant. So for example, if we want to find y, so we're trying to find the equation y, if we know that y prime equals 2x, well, it's pretty easy to say, well, if the derivative is 2x, then y equals x squared would be a solution. But I need to keep in mind that there could be a constant. So y equals x squared plus c. This would be the general solution. So this is a basic form of solving a differential equation. So what we're going to look at is this method called separation of variables. So with separation of variables, basically what I'm going to do is I'm going to get my common terms together. So I want to get my y squareds over here with dy, and I want to move dx over to this side of the equation. So this would be y squared dy equals -2 plus x squared dx. So the reason I say this is slightly controversial is dy over dx is not a fraction. It happens to work in this case. If you're in BC in class, we will give an in-depth explanation for why it works. If you're in AB, for now, you're going to have to accept that we can treat this as a fraction for the purpose of separation of variables to solve equations. So again, BC, we will make sure that we talk about this in depth. AB, if you would like an explanation, I would be happy to give it to you after class or sometime outside of class. But the reason this is helpful right here, that we have it written like this, is now we can integrate both sides of the equation. So if we integrate y squared dy, that's equal to the integral of -2 plus x squared dx. These are both pretty simple integrals to take. This is 1/3 y cubed equals -2x plus 1/3 x cubed plus c. If you notice, I only put plus c on one side of the equation. That's because technically with both of these integrals, they should have a constant added to them, but I could subtract the constant from here over to the other side. It all basically just gets absorbed into one single constant. So now all that's left is to solve for x, or sorry, to solve for y. So then this would be y equals -6x plus x cubed plus c to the 1/3. And so this would be the function for y. This would be the general solution, meaning that anything that has this form, this constant c could change, but anything with this form would give me this derivative for dy over dx. All right, so that's an example of finding a general solution. Now let's take a look at if we want a particular solution with an initial condition. The same beginning logic still applies. This is going to be e to the 2y, 2y, not 2d, e to the 2y dy equals 2x dx. Then we can integrate both sides of the equation. So we've got 1/2 e to the 2y equals x squared plus c. Pretty straightforward. Now we just solve for y. So we've got e to the 2y equals 2x squared plus c. Again, I'm not changing c here. I'm not writing 2c because it's just a constant. 2 times c is just another constant. So this is just still some constant that we don't know. So then y will be ln 2x squared plus c over 2. So now I'm going to look back at my initial condition. It says y of 1 equals ln of 4 over 2. So then I know that ln of 4 over 2 is equal to ln of 2 plus c over 2. So we can see from this, pretty easy to tell that c is equal to 2. So then my particular solution for this initial condition would be ln of 2x squared plus 2 over 2. And this would be my particular solution. So basically separation of variables, you separate x's on one side, y's on the other, integrate, and then if you have an initial condition, use the initial condition to solve for c. So that is it for today. Today we talked about separation of variables, the method. then solving with an initial condition. And BC in class, we're going to go through an in-depth explanation for why it's okay to treat dy over dx like a fraction in this case. So if you have any questions, make sure that you bring them to class. I hope you took some good notes, and I will see you in the next lesson. Have a good day.